Good morning, everyone. My name's Arthur, and I'm a sophomore here at Thayer. So I want to kick things off with a question. And I'm genuinely asking, I want you guys to actually think about it for a second. What does biodiversity sound like? I mean, we never really phrase it that way, right? Usually when we think of biodiversity, we picture something, whether that be, a rainforest, a coral reef, maybe one of David Attenborough's documentaries. But, the point I'm getting to is that biodiversity is always thought of visually. But while I'm standing up here, every ecosystem on Earth is producing a continuous acoustic record of its own health. Birds calling at the water's edge, whales singing across ocean basins, an entire Amazon canopy waking up before sunrise. We've been measuring the living world with our eyes for too long. Some of the most important real-time information about our planet's health is encoded in sound, and scientists are finally figuring out how to decode it. That field is called bioacoustics, and that's the topic I wanted to explore today. All right, so before we get into anything else, I want to try something. Close your eyes. I'm going to play 2 clips. That's it. Just listen. So for me, I hear song thrushes and European robins calling across the water, insects shuffling, wind moving through the trees. It's busy, it's layered, it feels full, right? Okay, second clip, you guys still need to close your eyes, but yeah. I mean, you could hear the wind, right? It's not silent necessarily, but something's missing, right? You all heard it, it feels simpler, emptier, And you didn't need a visual, right? You heard that something was wrong. Essentially, think of the natural world like a great animal orchestra. Think of a healthy ecosystem like a full orchestra. Every instrument has its own range, its own timing, and they're able to create harmonies within their surrounding environments. And now imagine, pulling out sections one by one. Like, the music doesn't just get quieter, it begins to lose its structure, right? That is the framework of something we call the acoustic niche hypothesis. It was developed by ecologist Bernie Cross, who gave us a 3-part framework scientists still use today to measure our acoustic landscape. Biophony, sounds from living things. Geophony, natural non-biological sounds. And anthrophony, the noise that we humans make. Over millions of years of coevolution, species carved out their own acoustic niches. And bioacoustics lets us hear that happen in real time. So I've been talking about bioacoustics a lot, obviously, so I'll give you a quick definition. At its core, bioacoustics is the study of 3 things: how animals produce sound, how that sound moves through an environment and is transmitted, and how it gets received and interpreted by scientists. In practice, researchers drop these autonomous recording units into forests, wetlands, deep ocean environments, and they're about, the size of a brick. They run for months, gathering more acoustic information than a team of field biologists could catalog in a year. Then, those recordings get turned into something called spectrograms, with time as the x-axis, frequency as the y-axis, and brightness showing the intensity. This specific spectrogram measures the call of a dunnock, a perching bird found in Central Asia. Scientists have begun to see patterns among distinctive species when looking at this data. A wood thrush traces a distinctive arc. A frog leaves a rhythmic pulse. You could record a chainsaw if you really wanted to, and it produces a smear that an algorithm can actually flag for illegal activity using AI. Bioacoustics gives you a continuous data stream, and that changes everything about how fast we can detect a problem in any ecosystem we monitor. So what can that data stream actually tell us? 4 things, and they build on each other. First is which species are present. The Cornell's BirdNet system can now identify over 6,000 bird species from raw audio alone, continuously, non-invasively, at a fraction of what physical surveys would cost. Second is population trends over time. You count calls instead of individuals, and across seasons, across years, at the scale of whole regions. It sounds simple, but it works so incredibly well. And of course, third, ecosystem health as a whole. Scientists can actually quantify the organization of specific harmonies, including something we call the acoustic complexity index, and it's become one of the most reliable proxies for biodiversity we have. A high complexity means a healthy ecosystem. If it's sparse or disorganized, we know something's wrong. And fourth, detecting human impact. Shipping lanes, drilling platforms, urban sprawl, all of it leaves measurable acoustic signatures. We're watching ourselves disrupt it in real time. Okay, I'm gonna get concrete for a moment because I've been throwing a ton of concepts at you. Let's backtrack a little bit. Here's a frog, but these desert rain frogs are among 7,900, well, up there it says 8,000, known frog species. Every single one has a unique call. I don't think you quite understand how much information is packed into a frog. The calling rate reflects the temperature, call structure tracks the water quality, breeding chorus times shift according to seasonal phenology. It's crazy, right? Over 40% of frog species are currently threatened with extinction. Frogs are what we call indicator species. Their health reflects the whole system. When frog calls start dropping out, that's one of the earliest signs we know that something is failing. That leads on to my next point. Bioacoustics doesn't just tell us when something's wrong, it tells us what's wrong. Take shipping noise. If you look at these 2 spectrograms, the first is of a southern resident killer whale's call. The second is of a common cargo vessel. Southern resident killer whales are critically endangered and on the brink of extinction, with fewer than 75 individuals remaining as of 2025. That's crazy, right? They communicate through low-frequency calls and carry hundreds of kilometers underwater. And they're essentially trying to talk over 173 decibels of ship noise that commercial shipping has created. Habitat loss is another big one. Parts of the Amazon that look lush and green can have a soundscape that's already collapsing underneath. Crucially, researchers have found that above ground biomass, like a forest, can look structurally intact, while its soundscape has already collapsed. So climate change is embedded in the recordings too. Dawn chorus is shifting earlier, tropical species appearing in temperate soundscapes, migration times changing year by year. These acoustic archives are becoming some of our most valuable long-term climate records. And of course, invasive species. The brown tree snake, infamously introduced to Guam after World War II, has wiped out most of the island's native bird populations. Entire frequency bands just go dark, gone, just like that. And bioacoustics can catch that happening early, sometimes before boots on the ground surveys even arrive. I'm running out of time, so the next decade in this field is going to be genuinely extraordinary. And I say that not as hype, but because the trajectory is already visible. AI identification is getting close to real-time species census capability, not just birds, but insects, bats, fish, marine invertebrates. A single device in a rainforest will be capable of generating a near-complete species inventory overnight. And acoustic restoration. Researchers at the University of Exeter played recordings of healthy reef soundscapes through underwater speakers. And fish returned at twice the normal rate. Sound wasn't just monitoring the system, it was actually drawing life back into it. And of course, citizen science. The Merlin Bird ID app. It's free, available right now on your phone. This isn't an ad, but uses the same AI pipeline as a professional acoustic monitoring equipment. You could walk into any pond here tonight and hit record for 30 minutes, and you can contribute real, authentic data to a real research network. I'm really running out of time, so let me leave you with something. The acoustic layer of our planet is ancient, and right now it's in trouble. But what I find genuinely hopeful is that we now have the tools to hear that damage early, before the population crashes, before it's too late to do anything about it. That's new. That matters. The barriers to participating in this science are basically gone. What's missing is just people knowing it exists. Perhaps we need to consider that the key to understanding and saving our ecosystem is simply learning how to listen. Thank you.